Before we begin, I need you to understand something about armor that most people get wrong. We think of armor the way we think of a wall. Thick means strong. You want more protection? You add more steel. Simple. But that is not how it works. That is not how it has ever worked. Steel is not one thing. Steel is a recipe. And like any recipe, the ingredients matter more than the quantity. A 3-inch plate of ordinary carbon steel will shatter like pottery when a shell hits it at 2,000 feet per second. The impact does not dent it does not bend it breaks it. The molecules in the steel cannot absorb the energy fast enough, so the entire plate fractures. Shards of metal fly backward into the crew compartment at lethal velocity. The armor that was supposed to protect the men inside becomes the weapon that kills them. In the First World War, the British learned this the hard way. The first tanks rolled into battle at the Somme in 1916 wearing 75 millimeters of manganese steel plate. It was heavy, it was slow, and when German shells struck it at the right angle, it cracked. The tanks survived, barely, but the armor was a brute force solution to a materials science problem that nobody had yet solved. The Germans, as it turned out, had already solved it. They just were not telling anyone. Deep inside the Krupp steelworks at Essen, metallurgists had been quietly experimenting with a metal that almost nobody in the industrial world had heard of. A metal so obscure it did not even have a proper commercial market. A metal that had been discovered in 1778, identified as a distinct element in 1781, and then ignored for the next 130 years because nobody could figure out what to do with it. That metal was molybdenum. The name comes from the Greek word molybdos, meaning lead-like, because the dark, greasy mineral that contains it, molybdenite, looks and feels like graphite or lead ore. For centuries, miners who encountered it assumed it was one or the other. Norwegian peasants who found molybdenite outcrops in the hills above a remote settlement called Knaben in the 1880s called it pencil rock because it left dark streaks on their hands, just like a lead pencil. They had no idea what it actually was. They certainly had no idea that it would become the most strategically critical metal of the 20th century. What Krupp's metallurgists discovered was that adding tiny amounts of molybdenum to steel transformed it. Not a little, profoundly. Molybdenum has a melting point of 4,753 degrees Fahrenheit, nearly 3,000 degrees higher than iron. When you dissolve even 0.5% of molybdenum into a steel alloy, the molybdenum atoms wedge themselves into the crystal lattice of the iron, locking the molecular structure in place. The steel becomes harder without becoming brittle. It resists heat without softening. It absorbs impact energy by flexing at the molecular level instead of fracturing. Where manganese steel shattered, molybdenum steel bent. Where ordinary armor cracked, Moly armor held. Krupp used this knowledge to build Big Bertha, the super-heavy howitzer that terrorized the Western Front. Big Bertha fired a shell weighing nearly a ton at a range of 9 miles. The temperatures generated inside the barrel by the propellant charge would have melted any conventional steel gun tube within days. But the molybdenum steel barrel held. It survived firing after firing, delivering destruction that the Allied armies could not explain and could not match. The Allies eventually captured German weapons, melted them down, and analyzed the composition. That is how they discovered the secret. Molybdenum, a metal they had barely heard of, was the ingredient that made German steel superior to anything the Allies possessed. But knowing the secret and exploiting it were two different things. Where do you get molybdenum? In 1914, there was essentially one producing mine on the planet for this metal, a small Norwegian operation at Knaben, and there was one enormous deposit sitting untouched on a frozen mountaintop in Colorado that nobody had figured out how to mine economically. This is the story of that mountaintop. A story about a metal that nobody wanted, a mine that nobody believed in, and a war that consumed every ounce of it the earth could yield. This is the story of Climax. In 1879, a prospector named Charles Center was picking through rock on Bartlett Mountain near Fremont Pass in the Colorado Rockies. Fremont Pass sits on the Continental Divide at an elevation of over 11,000 feet. The air is thin enough to make a grown man dizzy. The winters dub 300 inches of snow. The wind cuts through clothing like it is not there. Center had come looking for gold, or maybe silver, driven by the Leadville boom that was making fortunes 30 miles to the south. What he found instead was a massive deposit of dark gray rock laced with bluish-black veins. He had no idea what it was. It was not gold, it was not silver, it was not galena, it was not graphite, though it looked like both. He staked a claim anyway, more out of habit than hope, and did not bother to file it for more than a decade. In 1895, a professor from the Colorado School of Mines finally identified the gray rock as molybdenite, the sulfide ore of molybdenum. The identification generated exactly zero excitement. Molybdenum in 1895 was a laboratory curiosity. It had no commercial use, it had no market price. The Bartlett Mountain deposit, which would turn out to be the largest concentration of molybdenite on the planet, was worth less than the mule it took to get there. It stayed that way for 20 years. Then, the First World War broke out, and the Germans unveiled their molybdenum steel weapons. Suddenly, a metal that had been worthless was worth a fortune. Prospectors and speculators who could not pronounce molybdenum and certainly could not spell it stampeded to Bartlett Mountain. By 1917, 3 companies were fighting for control of the deposit. Among them was a syndicate backed by the American Metal Company of New York, which was 47% owned by Metallgestalt, a powerful German metals cartel. The irony was exquisite. The Germans had created the demand for molybdenum with their weapons, and a German-controlled company was trying to secure the world's largest supply of it from American soil. When the United States entered the war in 1917, the government invoked the Trading with the Enemy Act, seized the German-owned shares, and let the now Americanized Climax Molybdenum Company proceed. A crew of 250 men built the first mine and mill in 7 months, working at elevations where a normal person gets winded climbing a flight of stairs. In February 1918, coordinated operations began. On April 2nd, the first shipment of 25 tons of molybdenite concentrate left Fremont Pass on 2 special railroad cars bound for a Pittsburgh steelworks. The cargo was valued at $100,000. 2 armed Pinkerton guards rode with it the entire way. But the war ended 7 months later, and the molybdenum market collapsed overnight. Demand vanished, the price cratered. The Climax Mine shut down in April 1919 and sat silent for 5 years. It seemed like the story was over. A brief wartime boom, a bust, and a frozen mountain full of useless rock. It was not over. It wasn't even close to beginning. In the early 1920s, with the mine idle and molybdenum surplus flooding a non-existent market, the Climax Molybdenum Company made a decision that would have seemed insane to any conventional businessman. They started giving their product away. They donated molybdenum to steel companies, free of charge, begging them to experiment with it. Most steelmakers were not interested. The industry was conservative. They knew how to make carbon steel and alloy steel with nickel and chromium. They did not need a new ingredient that nobody understood. But one man took notice. C.H. Wills, an automotive engineer who had helped Henry Ford design the Model T, ordered a quantity of the cheap wartime molybdenum and used it to build a luxury car. Every load-bearing component of the 1921 Wills St. Clair, nicknamed the Grey Goose, was made from a molybdenum-bearing steel alloy. The car was lighter, stronger, and more durable than anything on the road. The Grey Goose became a rolling advertisement for what molybdenum could do. The Grey Goose was not a commercial success. It was too expensive, and Wills was a better engineer than he was a businessman. The company went bankrupt in 1926, but the car had served its purpose. It proved to the skeptics in the steel industry that molybdenum was not a wartime novelty. It was a genuine advance in materials science. Word spread. Engineers talked, papers were published, and slowly, the steel industry began to take notice. In 1891, the French company Schneider & Co. had been the first to use molybdenum in armor plate. But it was the interwar period that revealed the metal's true versatility. By the mid-1920s, metallurgists were discovering that molybdenum did not just harden steel, it improved nearly every property that mattered. It increased toughness, the ability to absorb impact without fracturing. It improved hardenability, the ability to be heat-treated to precise specifications. It enhanced corrosion resistance, heat resistance, and weldability. And it did all this in very small quantities. A fraction of a percent of molybdenum could transform the performance of an entire alloy. It was not a replacement for other metals, it was a multiplier. It made everything else work better. The Climax Mine reopened in 1924. By 1926, it was supplying 3/4 of the world's molybdenum. And Climax's engineers, led by a man named Max Schott, were about to revolutionize the mining industry itself. The challenge was the ore. The Bartlett Mountain deposit was enormous, but it was low-grade, containing only a fraction of a percent of molybdenite in each ton of rock. Conventional mining methods could not extract it profitably. Schott and his engineers developed a technique called block cave mining, a method so audacious it sounds like something from science fiction. They excavated a network of tunnels beneath the ore body, then strategically removed support pillars, causing the millions of tons of rock above to crush itself under its own weight and collapse downward into the void. The broken ore flowed by gravity into collection funnels, where it was loaded onto underground train cars and hauled to the mill. It was controlled demolition on a geological scale. They were mining a mountain by making it eat itself from below. The block cave system worked brilliantly. Costs plummeted, production soared. By the 1930s, Climax was posting the best financial performance of any American company during the Great Depression. While factories across the country closed and bread lines stretched around city blocks, the mine on the frozen mountaintop was turning a profit. But working at Climax was brutal. The miners called it the hell hole on the hill, and they were not exaggerating. The mine sat above 11,000 feet. The air contained roughly 40% less oxygen than at sea level. New workers arrived and could barely swing a pickaxe for the first week. Headaches, nausea, and nosebleeds were constant companions until the body acclimatized, if it acclimatized. Some men never adjusted. They left within days. The cold was relentless. Winter temperatures regularly fell to 30 or 40 degrees below 0 Fahrenheit. Snow buried the camp for months. In 1936, a blizzard isolated the mine for weeks, trapping workers and their families in a frozen siege that tested the limits of human endurance. Underground, conditions were marginally better. At least the temperature was above freezing, but the work was dangerous. Cave-ins, rockfalls, and equipment failures were routine. The noise of the crushing ore, channeled through the tunnel system, was a constant low rumble that men said they could feel in their teeth. The turnover rate was staggering. More than 65,000 people worked at Climax over its lifetime, but most lasted only weeks or months. The company, realizing that it could not keep miners if it treated them like expendable labor, invested $4 million in building a company town on Fremont Pass. They constructed single-family houses, apartments, a hospital, a school, a recreation center, and even a ski area. At an elevation of 11,450 feet, Climax became the highest human settlement in North America, the highest town on the continent, with the second highest post office and the highest railroad station in the United States. And then, war came again. By 1939, the world was rearming. Germany's Wehrmacht was rebuilding its military machine on a foundation of molybdenum steel. The panzer tanks that would blitz across Poland and France used chromium-molybdenum armor, a combination that made the steel hard enough to stop small arms fire, but tough enough to absorb the impact of anti-tank rounds without shattering. German armor typically contained between 0.5% and 2.5% chromium and 0.25% to 0.5% molybdenum. These sound like small numbers. They were not. They represented the difference between armor that stopped a shell and armor that shattered into lethal fragments. The Germans sourced their molybdenum from the Knaben mines in occupied Norway, which they seized immediately after invading in April 1940. One of the strategic reasons for the Norwegian invasion was precisely this: control of Knaben. Germany stationed roughly 1,000 troops around the mines and constructed a formidable ring of anti-aircraft batteries to protect them. The message was clear. Molybdenum was not just useful, it was essential. It was a material of war at the highest strategic level. And the United States had it. There's a detail here that most histories miss. In 1939, the Nazi-Soviet pact redirected Soviet manganese exports away from the United States and toward Germany. Manganese was a critical alloying element in American steel production. Losing access to Soviet manganese forced American metallurgists to redesign their alloy steels, and the solution they found was to use more molybdenum. Molybdenum-bearing steels could achieve comparable or superior performance to manganese-heavy formulations while using a resource that America controlled domestically. The Nazi-Soviet pact, intended to strengthen Germany's position, had the unintended consequence of making America more dependent on its own molybdenum supplies, which meant more dependent on Climax, which meant that when the emergency came, the supply chain was already oriented toward the one material America had in abundance. When the Federal War Production Board assessed American strategic resources after Pearl Harbor, they reached a conclusion that would have astonished Charles Center. The gray rock on Bartlett Mountain that no one had wanted in 1879 was now the top priority mine in the United States. The entire Allied war effort, every tank, every gun barrel, every aircraft engine, every naval vessel, everything that required steel strong enough to survive combat depended on molybdenum, and virtually all of it came from a single mine on a frozen mountaintop in Colorado. The War Production Board issued the order, Emergency Production. Climax was to operate around the clock at 150% of its design capacity. There would be no maintenance shutdowns. There would be no scheduled repairs. The mountain would give up its molybdenum, and it would give it up now. For more than 3 years, from 1942 through the end of the war, Climax ran without pause. Men worked in shifts that blurred into an endless cycle of drilling, blasting, hauling, and crushing. The block cave system, designed for sustainable extraction, was pushed to its absolute physical limit. The underground chambers were expanded faster than geology could safely accommodate. Rock bursts, sudden explosive failures of overstressed stone became more frequent. Timber supports that should have been replaced were patched and reinforced because there was no time to replace them properly. Above ground, the mill processed ore continuously. The flotation cells, which separated molybdenite from waste rock using chemical-laden water, ran 24 hours a day. The roasting furnaces, which converted molybdenite concentrate into molybdenum trioxide for shipment to steel plants, glowed around the clock. The railroad cars that carried the finished product down the mountain to the steel mills of Pennsylvania and Ohio ran in an unbroken chain. Security tightened overnight. A top-secret observatory was constructed on Fremont Pass. The entire mine was classified. Armed guards were posted at the entrances. Tourists driving over Fremont Pass on the highway had their cameras confiscated if they attempted to photograph the operation. Joan Kaufman Brookshire, who grew up at Climax during the war, later wrote that the town was encircled with a chain-link fence topped with barbed wire. Guards were brought in to track everyone who worked and lived there. Children were told not to cause trouble because if their fathers were fired, the whole family would be immediately expelled from the town. For a mining camp above 11,000 feet in the Colorado Rockies with no other settlement for miles, expulsion was not a minor inconvenience. It was an exile. The men who worked the emergency shifts at Climax during the war came from everywhere. Some were experienced hard rock miners from Leadville and Buena Vista. Others were farmers and ranchers from the Arkansas Valley who had never been underground in their lives. Some were too old for the draft. Some had been rejected for military service because of flat feet or poor eyesight or hearts that skipped a beat under exertion. They came to the mountain because the wages were good and the work was declared essential, which meant that a man working at Climax was contributing to the war effort as surely as a man carrying a rifle in North Africa. But the mountain did not care about patriotism. At 11,000 feet, the oxygen content of the air is roughly 60% of what it is at sea level. A man carrying a heavy drill bit down a tunnel at that altitude is operating at the physiological equivalent of running a race at lower elevations. Hearts pounded, lungs burned. Nosebleeds were so common that men carried rags in their pockets the way other workers carry handkerchiefs. Silicosis, the lung disease caused by inhaling fine rock dust, was a constant threat. The underground air was thick with particulate from blasting and crushing operations. Ventilation systems existed but were inadequate for the scale of emergency production. Men breathed the mountain into their lungs with every shift. The turnover was relentless. Workers arrived, endured a week or two of altitude sickness and back-breaking labor, and left. The mine hired continuously, a revolving door of desperate men feeding a desperate machine. Those who stayed, the old hands who had acclimatized and toughened, became the backbone of the operation. They trained the newcomers. They covered for the men who collapsed. They kept the ore flowing. The output was extraordinary. Before the war, American molybdenum production had already been climbing through the 1930s as civilian demand grew. But wartime demand dwarfed everything that came before. Global molybdenum production rocketed from roughly 100 tons during World War I to approximately 10,000 tons during World War II. Climax provided the overwhelming majority of what the Allies consumed. It was, in a very literal sense, arming the entire war machine. Consider what that molybdenum went into. The 4140 and 4340 series of chromium molybdenum steels became the workhorses of American military manufacturing. The 41XX steels typically contained around 0.15 to 0.25% molybdenum. These steels were used in gun tubes where they had to withstand the repeated thermal shock of firing. They were used in crankshafts and connecting rods for aircraft engines, where they had to endure thousands of hours of high-speed operation at extreme temperatures. They were used in tank hulls and turrets, where they had to absorb the kinetic energy of enemy fire without fracturing. The M4 Sherman tank, the backbone of the American armored force, rode on a hull made from molybdenum-bearing rolled homogeneous armor. The Sherman was not the best tank on the battlefield. Its armor was thinner than the German Tigers and Panthers. Its gun was less powerful. But the Sherman had one critical advantage that historians often overlook. America could build them. The moly steels used in the Sherman were designed not just for strength, but for manufacturability. They could be welded reliably, a property that molybdenum enhanced. They could be rolled into plates at standard steel mills without requiring exotic equipment. They could be heat-treated to consistent specifications across dozens of factories. Molybdenum made the steel not just strong, but predictable. And in mass production, predictability is everything. The numbers were staggering. The United States produced over 49,000 Sherman tanks during the war. It produced over 12,000 aircraft per month at peak production. It built hundreds of warships, from destroyers to battleships to aircraft carriers. Every one of those vehicles required molybdenum-bearing steel in its most critical components. The engines, the armor, the gun tubes, the landing gear, the structural members that held the wings to the fuselage, the boiler tubes in the warships, the crankshafts of the submarine diesel engines. Molybdenum was invisible. You could not see it in the finished product. It was a fraction of a percent of the total weight. But take it out, and the steel would fail. The gun tubes would erode, the armor would crack, the engines would seize, the aircraft would break apart in flight. Every weapon America fielded depended on a material that, for practical purposes, came from one mountain in Colorado. The Allies knew this, and they knew the Germans knew it, which is why the bombing of Nabben became a strategic priority. On March 3, 1943, 10 British de Havilland Mosquito strike fighters attacked the Nabben molybdenum mines in southern Norway. The raid damaged the facilities, but did not stop production. On November 16, 1943, the Allies returned in force. 130 American B-17 bombers from the 8th Air Force struck Nabben in a massive raid. The objective was not just to disrupt production, but to deny Germany access to its primary European source of molybdenum. The raids achieved partial success. Production at Nabben was disrupted, though the Germans managed to resume limited operations. But the damage was felt where it mattered most, in the quality of German armor. American ordnance analysts who examined captured German tanks later in the war documented a steady decline in the molybdenum content of German armor plate. Before 1943, German armor sections typically contained 0.30 to 0.55% molybdenum. By 1944, the molybdenum content had dropped to 0.15 to 0.25%. The most recently examined sections contained no molybdenum at all. The consequences were measurable. German armor became brittle. Tiger I tanks produced early in the war, when molybdenum was available, had armor that was both hard and tough. Tiger II tanks produced later, without molybdenum, had thicker armor but worse performance. Soviet tests on captured Tiger IIs found that the armor was not nearly as resilient as the earlier Tiger I. The steel shattered instead of flexing. The thickness was there, the metallurgy was not. As one wartime assessment noted, German armor quality declined progressively as the war continued. The early plates were excellent. The later ones were increasingly brittle and prone to cracking. The Germans tried to compensate by substituting vanadium and by adjusting their heat treatment processes, but nothing fully replaced what molybdenum had provided. A Tiger commander later admitted that German armor quality deteriorated because they ran out of what he called noble earths, the alloying elements that made good steel possible. Meanwhile, American armor held. The molybdenum kept flowing from Climax. The steel plants received their alloy. The tanks rolled off the assembly lines with armor that worked, because the recipe was right, because the ingredient that made it right was available in abundance from a mine that was tearing itself apart to provide it. The 3 years of emergency wartime production nearly destroyed the Climax Mine. The block cave system had been pushed far beyond its design limits. Underground chambers had been enlarged recklessly. Support structures were compromised. The mountain itself was showing signs of instability, with caving visible on the surface of Bartlett Mountain as the underground voids propagated upward. When the war ended, the mine was in desperate need of rebuilding. It got a brief respite before the Korean War demanded another round of emergency production, pushing the battered infrastructure to the breaking point once again. After Korea, Climax embarked on a massive modernization and expansion program. Metallurgists were discovering new uses for molybdenum beyond military steel. High-temperature alloys for jet engines and rocket motors required molybdenum because it retained its strength at temperatures where other metals softened to uselessness. The first generation of jet fighters, the F-86 Sabres and MiG-15s that dueled over Korea, flew on turbine blades made from nickel-molybdenum superalloys. Without molybdenum, those blades would have deformed in the searing exhaust stream. The turbines would have torn themselves apart, and the jet age would have been delayed by years. The transition from propeller aircraft to jet aircraft was not just an engineering achievement, it was a metallurgical one, and molybdenum was at the center of it. The Cold War created demand that dwarfed even the Second World War. Nuclear submarines required molybdenum-bearing steel for their pressure hulls, steel that could withstand crushing oceanic pressure at depth without cracking. Intercontinental ballistic missiles required molybdenum alloys in their rocket nozzles, components that had to endure temperatures exceeding 4,000 degrees Fahrenheit for minutes at a time. The space program consumed molybdenum in quantities that the wartime planners could not have imagined. And then there were the civilian applications. Catalysts for petroleum refining used molybdenum compounds to remove sulfur from crude oil, a process called hydrodesulfurization that made cleaner fuels possible. Molybdenum disulfide, the same compound that Norwegian peasants had once called pencil rock, turned out to be one of the finest solid lubricants ever discovered. It was used in engines, gearboxes, and industrial machinery wherever metal surfaces slid against each other under extreme pressure. Pigments containing molybdenum produced brilliant orange and red colors used in paints, plastics, and ceramics. And fertilizers benefited, because molybdenum turned out to be an essential trace nutrient for plants, a cofactor in the enzymes that allow plants and soil bacteria to convert atmospheric nitrogen into usable nutrients. The metal that had been a war material was becoming an indispensable component of modern industrial civilization. By By 1957, with 1,800 employees mining and milling 35,000 tons of ore per day, Climax was the largest underground mine in the world. The company town, perched at 11,450 feet, had grown to nearly 2,000 residents. But to accommodate further expansion, the town was moved, building by building, 12 miles down the hill to Leadville. It was one of the largest relocations of a community in American history. An entire town disassembled and trucked down a mountain road so the mine could grow. By the 1970s, 3,000 Climax employees were processing 50,000 tons of ore per day from 3 underground levels and a new open pit, the highest open-pit mine in the world, with its upper benches above 12,000 feet. Equipment had to use special lubricants that would not freeze. Engines had to be modified for the thin air. Men worked in conditions that would qualify as extreme by any mountaineering standard. Over its lifetime, Climax mined more than 500 million tons of ore and recovered over 2 billion pounds of elemental molybdenum. A single mine, on a single mountain, in a single state, produced one of the highest single mine value outputs in the history of mining. Then, in 1981, the molybdenum market crashed, and the story of Climax entered its final act. Today, molybdenum is the invisible backbone of the steel that holds the modern world together. About 80% of all molybdenum produced goes into steel alloys. It is in the stainless steel of surgical instruments and kitchen sinks. It is in the structural steel of skyscrapers and bridges. It is in the pipelines that carry oil and natural gas across continents. It is in the turbine blades of jet engines that operate at temperatures exceeding 2,000 degrees Fahrenheit. It is in the catalysts at petroleum refineries that remove sulfur from fuel. It is in the fertilizer that helps feed 8 billion people. Because without molybdenum, the nitrogen cycle breaks down and crops starve. It is even in your body. Molybdenum is an essential trace element for human life. Enzymes containing molybdenum process sulfur-containing amino acids and help your body detoxify harmful substances. You carry a few milligrams of the war metal in your cells right now. The element that armed the world turned out to be essential to feeding it and keeping it alive. The global production of molybdenum now exceeds 250,000 metric tons per year, produced from mines on 5 continents. China is the largest producer, followed by the United States, Chile, Peru, and Mexico. The single-source dependency that made Climax the most strategically important mine in the world during the Second World War no longer exists. The supply chain has diversified. The vulnerability has been distributed. But during those years, between 1941 and 1945, it was not distributed. It was concentrated in one place, on one mountain, in the hands of a few thousand men working above 11,000 feet in conditions that would break most people. Those men did not fire a shot. They did not fly a bomber or drive a tank. They stood in underground tunnels at altitude, breathing thin air and stone dust, drilling into a mountain that was collapsing around them, extracting a dark gray mineral that most of them could not have explained the importance of if you had asked. But without what they pulled from that mountain, the steel did not work. The armor cracked, the gun tubes eroded, the engines failed. Without molybdenum, the entire industrial arsenal of democracy was just iron with good intentions. Molybdenum was the ingredient that made American steel. Not more steel, better steel. Steel that bent instead of breaking. Steel that held under fire. Steel that could be welded and shaped and mass-produced in quantities that overwhelmed the Axis powers, not just with numbers, but with quality that their depleting molybdenum supplies could no longer match. Consider the asymmetry. By 1944, American factories were producing war material at a pace that beggars imagination. Tens of thousands of tanks, hundreds of thousands of trucks, hundreds of warships, planes beyond counting. Every critical component made from alloy steel that contained a fraction of a percent of molybdenum.
The stuff flowed like water from Climax down the mountain to the steel mills, and then into the weapons that stormed the beaches at Normandy, that island-hopped across the Pacific, that broke the back of the Wehrmacht in the hedgerows of France and the forests of the Ardennes. On the other side, German metallurgists watched their molybdenum supplies dwindle. They watched their armor quality degrade. They watched their gun tubes wear out faster and their engine components fail sooner. They tried everything to compensate. They adjusted alloy compositions. They modified heat treatments. They substituted vanadium and increased manganese. Some of the substitutions worked partially. None of them worked completely. The invisible ingredient was missing, and nothing could fully replace it. The Climax Mine won the Army-Navy E pennant, the coveted award for excellence in wartime production. It was one of the highest honors a civilian operation could receive. The miners accepted it and went back underground.
There is no monument to molybdenum at Normandy. There is no plaque at Iwo Jima crediting the metal that made the armor work. You will not find molybdenum mentioned in the speeches of Churchill or Roosevelt or in the memoirs of Eisenhower or Patton. It was too small, too invisible, too far down in the chemical composition of things to be noticed by anyone except the metallurgists who specified it and the miners who dug it. But it was there, in every tank that rolled off a landing craft, in every gun barrel that held its shape after 1,000 rounds, in every aircraft engine that ran hot for hours without seizing, in every warship's hull that absorbed a torpedo strike and stayed afloat. A fraction of a percent, an element most people cannot pronounce, mined from a mountain most people have never heard of, by men working in conditions most people cannot imagine. The story of Climax is a story about what it means to be indispensable and invisible at the same time. It is a story about how the great dramas of history rest on material foundations that nobody celebrates. You can have the bravest soldiers, the most brilliant generals, the most sophisticated battle plans. But if the steel breaks, everything breaks. If the armor shatters, the men inside die. If the engine fails, the bomber falls out of the sky. The metal that prevented all those failures was molybdenum. And for the 4 most critical years in the history of the 20th century, virtually all of it came from one place, a frozen mountain in Colorado where a prospector looking for gold found a gray rock he could not identify and did not want, and where 60 years later, thousands of men worked around the clock in the thin air above the Continental Divide, pulling from the earth the invisible ingredient that held the Allied war machine together. A fraction of a percent. That is all it took. A fraction of a percent of a metal nobody had heard of, from a mine nobody could find on a map, at an altitude where nobody should have been working. And without it, the steel did not hold, the armor did not protect, and the weapons did not work. Molybdenum did not fire a single shot, but it was in every shot that was fired. It was the ingredient nobody saw, in the steel everybody depended on, from the mountain that armed the world. And somewhere on that mountain, if you drive over Fremont Pass today on Colorado Highway 91, you can still see the scars. Bartlett Mountain is no longer the shape it was when Charles Center found it. The block cave mining hollowed out its interior. The open pit mining carved away its surface. The subsidence from decades of underground extraction has left visible depressions and fractured ridgelines where solid rock once stood. The company town is gone, moved to Leadville decades ago. The school, the hospital, the recreation center, the ski area, all dismantled or demolished. The highest town in North America exists now only in photographs and in the memories of the people who lived there. But the mine is not dead. In 2012, after a $750 million rebuilding program, Climax resumed production. New open-pit operations now process 25,000 tons of ore per day, producing roughly 30 million pounds of molybdenum per year. The mountain still has molybdenum to give. The market still needs it. The miners who work there today do not think about the Second World War. They do not think about Tiger tanks or Sherman armor or Big Bertha. They think about production quotas and ore grades and the weather forecast, which at 11,000 feet is always a matter of survival. They go underground or into the open pit, they do their shifts, and they come home. They are doing exactly what the men before them did, pulling a gray metal from a frozen mountain so that the steel of the world can hold together. The names change, the equipment improves, the purpose remains the same. A fraction of a percent. That is the amount of molybdenum in a typical alloy steel. A fraction of a percent that separates armor that protects from armor that kills its own crew. A fraction of a percent that separates an engine that runs from an engine that seizes. A fraction of a percent from a mountain that nobody wanted, for a metal that nobody understood, that turned out to be the difference between winning a war and losing one. The Climax Mine armed the Allied war machine, not with bullets, not with bombs, with a few thousand tons of dark gray powder that made everything else possible. And it did it from the top of the world, in the thin air above the continental divide, where the wind never stops and the snow never fully melts, and where the men who dug the metal that won the war went to work every day in conditions that would break most people, and came home every night to the highest town in America, and never once appeared in a history book. Until now.